not sure how much you know about us and what we're doing, but me and Bogdan, we are working in a VFX company from Belgrade. Artem is our friend. He's some super genius guy in VFX.
That is an intro for you too.
Yeah, and so we came here to show you because I guess you're all studying mathematics or something like that. And I guess since you're here, you have some interest in VFX and art or something. So we will try to present to you what we would say is the best way to combine the two and to like try to make a career in some technical arts, right? Okay.
Yes, it's
Good.
a good intro, I think. So
Thank you
we
very
could
much.
start.
I practice it.
Yes.
My mirror.
I was planning to take this one. Can I take it? Okay. Do this. Together.
So, okay, so practical application of mathematics in VFX. Good. Basically, as in life, in VFX, everything is mathematics. So, after all, all we do is deal with 3D coordinates, we calculate vectors, move things in space, of course. So knowing mathematics is not really necessary for VFX, but can be really useful. And for people who know maths and who are like studying that type of, who have the mathematical background, it's really easy to get into that kind of let's say algorithmic way of doing things. So also I have here some pictures that represent, like, as you would know, everything in nature is organized by mathematical rules, and you can simply use those rules if you have the right tools and knowledge how to use them. You can use them to make everything you want to make and to make it look realistic and cool. After all, that's what we try to do. So, in general, there is two types, two ways of doing things. You can do things manually, you can do things procedurally. Manual work, it's simple. However, many times you have to do the same things. You always do it. You always invest time. It can be time consuming. It is time consuming. It can be repetitive. It can be dull. We like to focus on more procedural approach. So what is a procedural approach? So that is, you make the program and you let it do the work for you. Like, you can chill or do whatever you want while your program works. Okay. The software we like to use for this type of algorithmic procedural VFX design, is called Houdini. Why do we use Houdini? Well, it's node-based, it's procedural, it has a lot of qualities that we can use to make whatever we want to make. So, what does it mean node-based? What does it mean procedural? We'll go through all of that. Proceduralism and nodes. So basically, in our line of work, the workflow is, in general, you make the algorithm, you have inputs, the algorithm processes those inputs, and it gives you some output. That's the baseline of what we do. So, with the idea is that if you make this algorithm, and it's a good algorithm, you can switch the inputs, and it will produce different results based on your inputs, and basically, you have done a lot of work with minimal effort. Good. Okay, so what are the nodes in the node-based software? So nodes are basically the operators. That would be the building blocks of our algorithm. So nodes in Houdini, well, they are basically small algorithms in themselves, but they can connect to become larger nets of algorithms and do more complex stuff. So basically what they have here is a showcase. Yep. It's a sphere, it's a cube, and it's a tube. And they all can connect to this little node down there. And that node basically scatters 1,000 points on each of them. And you switch and you get the same result on different output. That's basically the core idea of what happens. This is an example of a more complex node network. Cool. Okay. So, we said what I was talking so far about is the general idea of the workflow, so how you manage stuff. But the other thing that is really cool about Houdini is how it handles its geometry, how it handles what you have, and how it represents it to you in a beautiful way. So in Houdini, not sure how many of you have any experience with VFX in general.
Put up your hands on.
You've done before?
Yes.
Oh, incredible. Okay, so you know, what were the softwares you have been using so far? Houdini?
How many Houdinis?
How many Houdinis? Oh, damn.
Yes. So we have enthusiasts here.
Okay, that's cool. Okay, then you will find my part boring, but you'll find their part interesting. But who has no idea what Houdini does? I'm preparing you.
Do you want to see who has no idea?
Who has no idea?
For some boost about Houdini.
Okay,
It's fine.
you are the target. So in Houdini represents everything as points and primitives. What would be the primitives? Primitives are like the smallest chunks of geometry that can be represented by their position and size and orientation, and that a software can handle to create larger geometry, right? And everything, even those primitives, can be represented as points in Houdini. And what are points? Points are basically just the point positions in 3D space. They need their position attribute to exist. And those points, what's also really important, cool, can have attributes. Those are like types of information. That's the pieces of information that the position in space carries. Something like that. Everything we do in Houdini and everything everyone does in Houdini is represented in a geometry spreadsheet. This is an example of a geometry spreadsheet. So you basically, it works like Excel, but a really strong Excel. So in a geometry spreadsheet, in a nutshell, each row represents a point. There is a geometry spreadsheet for points and for primitives, and I'll show you with the video. It would be a lot better that way. Okay. So next slide. So here we have a grid. It's a simple 5 by 5 grid, and how much you see, I'm not sure. But, sorry. Okay. But yeah, it has 25 points and it has 16 primitives. So this is a spreadsheet for points. You can see 25 points, you can see their positions. These are 16 primitives. You can't see anything because the information about the positioning of primitives is hidden within these intrinsic attributes. We will not go there now. Sorry, I have a problem with stopping the video. It's a really major problem for me right now. Don't stop them. Okay, here I've given the attributes to my, I have to go fast. To my points. So now the points have these color attributes, which are shown as vectors, obviously, as all colors are. And now I just switched it to be primitive attributes. So each face has now a color attribute, which is now represented within the geometry spreadsheet of points. Maybe I can just stop it here.
You could stop it maybe here.
No, we switched.
We switched.
Yeah.
Let's just
Weird. Okay. Yeah. The train is gone for opening Houdini. Yeah, okay. So let me just, okay, I've actually done with this one. So this is one sphere. It is also a primitive. So you can see it's represented by 1 point and it's one primitive, even if it's a sphere. So yeah, within the spreadsheet there is one primitive and 1 point. Okay. So you can see sphere can also be made of smaller primitives like faces. Okay, now we have more points and more primitives. Cool. So what is I cannot work this. So what is also cool as this volume is also a primitive. Okay. Now this is a little VDB volume, which is in Houdini also represented by one pointer. This is really powerful because one point you can move really easily, and whatever is stored within that point can get moved the same way, easily and cheaply. So what is a VDB? Basically, you can imagine it like if you take this red cube and like divide it into a bunch of smaller cubes, and then into each small cube you give a value from 0 to 1, and that would be like this white fog. When there is 1, there is white fog. When there is 0, there is nothing, and they're all everything in between. So cool. Okay, and now we have this new type of primitive, which is a VDB. Okay, I guess.
So everything is fine. We obtained the mouse.
Great.
So it
Now
should
this is
work now.
the thing. Okay. Okay, great. So, what I did here, after I showed you this, that everything is one point, I kind of made some noise attribute. So yeah, I was talking about the density attribute. So when you have the name attribute in Houdini, it's like identifier. So it says, okay, do to this, whatever is named density in this point, do this to it. And what we did is like, remember the values I told you about? We just kind of multiplied that with random numbers, and then we got like this perforated fog. That's cool. Okay. And what's also cool is that this can be animated, of course, and even animated and perforated and multiplied and everything, it behaves as a one point, and you can manipulate it as one point, which, yeah, will be shown when I kind of transport it around like a point. Cool. Wow. Incredible. So yeah, that's the most boring example in the world, but I will get to the fun run right now. So cool. Instead of like multiplying the values, this other node is like some more complicated math, and it kind of scatters it around and moves those voxels around. So we can make some noise here to try to get some cloudy look from this sphere. And I think we are happy with this, yeah. So since it is a point, we can kind of scatter it as we did before with that scatter node, scatter it at any surface, and like get a bunch of those that are all behaving, that are all basically calculated within the software as instances of one thing. So it's really cheap to do. So here I have this grid, and here I am like destroying the grid to make it terrible, and here I'm like further destroying the thing. Doesn't matter what I do there. This is some general workflow in Houdini on the side. So yeah, further destroying, but that doesn't matter. It's terrible because I just scatter points onto it, and then I will use those points, and that's all I need. I just needed some mesh. Okay, and there is this super powerful thing called copy to points, and whatever we input from one side and the other side, it does this. So it gets copied to points, as the name says. So now we can like play with. It's also a cool thing I'm doing here. You can like make the whole system and make it look terrible, and then just have a final output, and then just play on the previous things. You don't have to have anything set until you have your working algorithm, and then just play and make cool effects from that. So cool. Okay. Currently, yes, but they don't need to be instances. But in this example, they are instances. I made them instances. I think Bogdan will have more to say about that. So yeah, this looks like a cloud, or it looks like a cotton field. I guess it looks more like a cotton field. So we don't like it. We don't like that this part of the cloud is so round and like spherical. So let's try to like switch the input to something more fun. Okay. So here I made this squashed sphere, and then I kind of destroyed it to make it more cloudy looking, incredibly cloudy looking. Yep. And when I pass it through the same little algorithm, it just does the same thing and outputs a bit different results. So now this cloud looks a bit better, but it's still kind of repetitive, and it can be better. And how do we do that in this particular example? So, slippery slope, that's what they call it. Yeah, this is, oh, I know what. So this is the spreadsheet for our scattered points. They have no attribute because they're just points. We have given them no attributes, and we can give them some attributes. So this node is basically a, now, okay. This node is basically giving a random p-scale attribute to each of the points. P-scale is one of the attributes that Houdini recognizes and knows what to do with it. So basically it's a point scale, the size of the point. Points are points, they have no scale, but this node can read the p-scale attribute and make those little clouds bigger and smaller. So you have some randomization there. I think we will, it's not super visible here, but I will make less points so it will be more visible. Yeah, so you see clearly that some are bigger, some are smaller, and that's all on the point attribute. So now it looks better, but it still is uniform. It has like these shapes everywhere appearing again and again. So would be great if we could have some kind of, if we could give them some random orientations, and we can, of course, with this orient attribute, which is a 4 attributes, because it's a quaternion, I'm not the one to speak about that. Okay, so it's basically random, telling them randomly where is up, where is front, where is side, and all of that. Okay. So after all that, we get something that for the amount of effort put in, it looks like a really nice cloud, if you ask me. Don't ask me. Yeah, but I still like it. You cannot if you don't want. And the cool thing is, if you want to see those rotations and stuff, you can just put it into a tube. The thing is here, you can work with the simple geometry. You don't need to, if you have super heavy, like little cloud, you can switch it to whatever, make the whole thing, and just at the end, reconnect it to whatever you want, and that's the procedural beauty at work. Nice. Very nice. Okay, next one. So the other thing that we didn't touch, and what is really one of the most powerful things in Houdini, is the existence and the availability to you as an artist of VFX. What is a VFX? VFX is a programming language of Houdini, which is given to you to use with this beautiful attribute triangle node. So this node, basically what it does, it iterates whatever is put into it. It can iterate through points, it can iterate through primitives. So basically, it does it's a node for writing code. So by itself, it does nothing, but you can write whatever code you want, and it will execute the code on each point iteratively. You will probably understand. So that's how you can make your own custom node. And the VOPs, represented with this other node, is basically a visual representation of VFX. If you don't like writing code, you can just like put nodes around that would do the same as a code. And example here. So here I have this sphere, and I've put it through attribute triangle, and I've put it to point VOP, and it's basically the same thing. What is done here, I've made this random attribute, put it in spreadsheet, and kind of multiplied points with random numbers. Okay. And in the VOP, it looks like oppa. In the VOP, it looks like this. So yeah, you have a position, you have a multiply, you have a random number based on the point number, and then you output the point, and you output this random attribute. Okay. So that's two ways of doing things, the vector operators. Cool. And within the spreadsheet, it's the same. You see on each point, we have this random attribute. And interesting thing about this random, which you probably are aware of, by now, is that it's pretty constant. So both of our random operations give us the same exact numbers for each point. Then that's why the results can be constant. That's in graphics, in computers generally, I think. Okay, right, Reynolds algorithm. So this is a kind of a story about flocking. Right, who knows about the Reynolds algorithm? It would be bad if you all do, like I would have nothing to speak about. But you don't, great. So it's an algorithm that describes flocking behaviors. Why is it here? Well, one of the first things I did, by profession, I'm a biologist. I studied biology and I have a master's degree in biology, and then I decided I will not get super rich by teaching geometry. I'm getting richer than with biology I used to do. So I decided I am going to be a programmer, as everyone decided to be, and then I decided that I like VFX. So I came into Crater, into our company, to be a practicant for Python IT position. And then the company got this super cool project with a lot of biological stuff, evolution, DNA, animal stuff. And I was like, yeah, I need to be in this thing. So there was this flock of fishes, and that needed to be simulated. And I kind of had free time because I was a practicant, nobody was looking at what I'm doing, and I just kind of messed around. So at that point, I didn't know anything about Houdini, so I just found a tutorial, of course. And I found that there is this Reynolds algorithm that is basically a model for describing the behavior of flocks and crowds. So everything, fish, bird, sheep, human, sheep, behave basically by the three simple principles when in flocks. So principles of the algorithms and that behaviors are three. One is stay close to your neighbors. Second is don't get too close to your neighbors, meaning don't hit each other. And the third one would be don't move in the general position of your neighbors. So that is simply, very simply, a simple mathematical model that gives really good and organic results. So I was like, okay, let me try. So I did this. This was and of course, this is nothing I invented. It's invented multiple times. But I found this tutorial of the Japanese guy who kind of implemented this Houdini, and I was like, okay, let's try it. So here we have the sphere as we had before. Here we have giving it some volume. And again, we have the scatter, which is now scattering is in volume because it's working on the volume. This is the first time we see wrangle in action. So this wrangle only sets the initial attributes for velocity, acceleration, and some other attributes. So you see that it's exactly what it does. Set attributes and points. Okay, cool. It was also cool to note that these guys, so you can make a parameter, and within this VFX node, you make a parameter, you can have external control of the variables within the code. Cool. Okay. You can also make an external node and control the other nodes with that node. This is not important. And yeah, so here I made this node that does nothing. I gave it some parameters and I connected all those, so you can use this node as a controller to various things you want to control, like the size of the initial flock, like the number of fishes. Yep, cool, very cool. So that's it. And this is a solver. Haven't mentioned solver so far. Who has an idea what a solver is? Okay, cool. So to do simulation, and Houdini is mostly used for simulations, you need solvers. What is a simulation and what does solver do, and why is it special compared to other methods of working, like procedural animation? Is that it has access to this previous frame. So what it does, basically, it takes the previous frame, and based on the information on the previous frame, it calculates the next frame. in our position, it calculates the position of fishes within in frames. So cool. Okay. So let's see what we did with that here. As we said, 3 rules of behavior. Separate from your friends, don't hate your friends. Align with your friends, go in general direction, and cohesion, like go with them. And all of these nodes are like some simple basic code, which we're not going to go through today. It's a topic for another time. And then basically all we do here is calculate this acceleration attribute, and in this update node we like say, okay, update velocity, add the acceleration that is calculated here on the velocity, then add that velocity to position, and then position moves from frame to frame in the direction of the velocity. Cool. Very nice. And it's all that. And yeah, the last code is just don't go too far. When you go here, just go back. No, yeah, no. Just don't let the fishes escape from the pond. Because they're mad, they like go whatever they want. So yeah, you see nothing here, but you will. Yeah, cool. So this is what we made with these 3 simple nodes. It's nothing much, but it's an honest work. And what happens within the spreadsheet is this. Basically dancing numbers. Things are getting constantly calculated, and that's what produces our movement.
Actually, you can predict the position.
Well,
dancing numbers you can actually, like he does.
Well, of course, if I do the maths up front, I could predict probably, but I never had the need to do that. So yeah, now we had here we made our movement, and now we are going to make it look better, like make it look fishy-like. So we have this node that, like as its name says, leaves the trails from the fishes, from the points. And now we have this node that will make those trails into lines, not important. We are putting some attributes there, which is also not important for this time. Yeah, it's just schminka. Cool, dancing numbers. I guess at this point I was like, let's look at the numbers. So, if you ask me, this simple thing looks really organic, and I really like it. Basically, in the end, moral of the story. In the end, I just decided, I just found out that Houdini already has a tool for this type, and that I didn't need to do any of this. And I just scraped this thing, but it was enough to give me a job, and it was a cool learning experience, to be honest. So yeah, fishes. Cool.
Let me see it. MNH. Okay, so this is also one thing that MIloš did. This project, we will present this project I think in September. Right now it had premiere in New York. It's American Museum of Natural History. So, like logically, MIloš was tasked to do this thing as well. So there is one like workflow thing that we had here. Like we had people in the studio who were tasked with creating texture for this leaf, and like naturally, if you are junior, you would take some photos and try to make best texture in Substance Designer that you can. But basically, resolution that you would need for this would be insane. So what we did is basically to split this task. One part will be somebody who is like a texture painter who will do this texture, and the other task was given to MIloš. So we transition to the part of the leaf that is fully procedural. These veins that he did are based on the veins from the texture of the leaf, but all the other stuff you see like tiny chloroplasts, and all of these cells have like unique simulations of these cells moving inside. And the thing about Houdini is we had like thousands of these cells, and we could put it on the farm of 100 machines, and it would come out like this was really fast, like coming up in half an hour or something like that. Okay, so my task will be to guide you like further down the line, down the layers of Houdini. So what Miloš showed was what you can do in this SOPs level, so manipulating geometry, and he showed you a little bit of DOPS, which would be like like doing simulations, and Artem will explain you more later. And I will go a little bit further down. So I will show you a couple of examples of things that I did in VFX. So this would be like one example, really simple task that you all can try. Okay. So we want to do some rippling on the geometry, and we know something about trigonometric functions, and basically inside of VFX, of course, like in any other software, there is sine wave function. So what I'm doing here, I'm writing simple VFX code, which would basically transform y position of this line based on the sine wave, and input would be x position of this line. So this is example of the simplest thing that you can do in VFX. Okay, and here I'm promoting some parameters. I don't know how well do you see. I'm promoting some parameters that you would use to control this function. Okay, like frequency and the offset. And basically you can animate these things. And I think I added some decay in the end. No, this is like just global amplitude, like multiplying everything in the end. Yeah. So you can write code and promote parameters that you assume somebody who is more artistic will use to control the effect. Okay. Do you understand this? Okay. Next thing. So if we translate this to like XZ plane, this is how it would look. Okay, so basically what we can do, we can take distance from the zero and run that distance through the sine wave function and get like pretty similar thing. And we can use that to control third axis of this plane. Yeah, I think code here is a little bit smaller. But it's the same thing. It's nothing special. Okay. Yeah. And basically, I'm writing this, and this is this program. This program is running on each point on this geometry, totally multi-threaded. So whatever you write, it will be multi-threaded, like using all CPUs that you have, which is important. Okay. And what is really cool about VFX is same code with some small modifications you can put inside shaders. So as you see, this is a plane that has, this is one primitive 4 points. So there is no dense geometry here. So I'm running the same code for this ripple inside the shader. And it's running very fast. So basically, I'm writing displacement shader here for this. And you might ask, like, what is the use of this? So imagine that you have a bunch of points in the space, and you want to splatter a bunch of textures on your model without thinking about UVs. So, for example, you can do this kind of stuff. Okay, and this is practical example of this effect. So, back when I was FX junior, we had hired one guy to do this effect, and he was taking 2 months to write fluid solver that would, like, with the physics that would put these points in proper position and they would not explode and blah blah blah. And he spent 2 months of our time and he couldn't do it. So I was tasked, when he was fired, I was tasked to do this, and I was junior. So my result was this. And when we showed this to client was like, okay, finally you showed me something that is like the thing that we agreed in storyboard. So basically the thing I showed you with the ripple is the same thing here. So the only difference is I'm not affecting Y position of these points. I'm doing something different. Basically, I'm representing these points as, so you can represent them as points with X, Y, Z positions, but I represented them as normalized vector times distance from 0. So what that allowed me to do, oh no, this is not that example. Okay, this is something other. This is cross product. You all know what cross product is. No? You should. Okay. When somebody wakes you up in 3 a.m. cross product, you should know that. So, yeah, so here I'm using cross product in order to shape velocities of these points, so I can create like small tornado. And why this is cool? You will, when you do stuff in Houdini, oftentimes you will do like fires, explosions, water explosions, and so on. And oftentimes you will get comments like, can this water move like this? And director will write or draw some lines. So you will be tasked with the task to like force things to move in some way. And we do that with the help of velocity fields. Okay. And these are some examples of this. So this was my like FX junior things, and I didn't know anything about fluid simulations back then, so all of that water was done with regular particles, no fluid dynamics. Yeah, so some strange Chinese film. Okay. Okay. And after that, I was tasked on one project to create like procedural arena. So, and I was not the one that should build that arena in the end. So I was just tasked to create a tool that some other artists will use to generate it. So this was my result. And what is really great thing? I packaged up all of my stuff inside of this tool, and in Houdini, that your like custom tools are called digital assets. And what you can do without any modifications, you can load this tool inside Unreal, inside Unity, inside Maya if you want, inside some other engines as well. And basically, you can design, like, for example, generator for roads, generator for buildings, for whatever. And if you saw these demos from Epic, in which they did like New York type of the city for Matrix demo, basically this was the technology they used to generate city. Okay. And yeah, so here in that tool, I did a bit of X, and I was trying to find like how to generate stairs. And all of the tutorials were suggesting to take a plane that has thousands of points and procedurally move these points. But what is the problem with that? Problem is you have to create like 10,000 points in order to generate stairs. So you see, if I lower the number of points, I lose the stairs. So I'm generating a bunch of points that I will not need in the end, and I will have to figure out how to get rid of these points that are in line, which is not so hard to do, but it's stupid. So the other approach I did is basically I took empty attribute wrangle, and it has mode in which you can do geometry from scratch. So that other approach was really simple, like create for loop that would walk up and create points, and that is also tied with the parameters of the stair height, total length, and total height. So if you want, you can generate geometry from scratch, like creating points, creating lines, creating primitives, creating volumes, whatever you imagine, you can create it from scratch. Okay? And then we had, this was like 2 days ago, a colleague of mine was tasked to take some OSM data of the roads and create intersections and to create geometry, proper geometry for these roads. So his artistic approach was, okay, can I just merge all of these points together and then smooth them a bit, and then try to like convert everything to points, find connections, and that is something that he got. It looks more organic than it looks like a streets, and that is approach, like when you don't know like what you are doing, you are trying to combine some things in order to get to results, and that thing can work sometimes, but there is better approach for this. So what I figured out is all of these street sections are just polygons with 2 triangles. So I created a small VEX code which would find what is the longest edge on these polygons and create line in between. So this was what I got. So a little bit of VEX code. And then I got intersections. So these are just intersections, and yeah, I'm trying to show it better. So we got 3 lines for intersections, and if we try to connect these points, we get this. Because these points, the order of these points is very random. So what you need to do, you need to sort them either clockwise or counterclockwise. So there is a really convenient function that's called 8N2, with which you can represent these points like relative from the center as vectors, and basically sort them out. So when we sort them, this is what we get. So we get proper connections, and then next step for this will be to create bands on these sections, but I don't have that now. Okay, so next thing would be why should you write simple render engine? Render engine like some really simple engine from 90s. And there is good tutorial for this. So if you think about rendering, what is happening, you have lights that are emitting some photons, and these photons bounce around the scene, and you get your image. So if you take this approach, this would clear never. So you will have to wait ages in order to get clear image from this. Okay, so this is like one idea. So this is just regular particle simulation that is leaving some points when they hit some surfaces. Okay, so then I got the idea. Okay, why wouldn't I write some simple render engine? So this is what I got, and so basically from this camera I'm generating points here, and these points are basically telling me like what should be illumination and what should be color and everything. Yeah. Okay. So this is the way it works. So I create an array for these pixels, and I have information about the center of the camera. So we shoot some rays from the camera center, and these rays hit some points in the scene, and these are the positions of these points. And basically we plot these positions onto that 2D grid. So these are positions of these points represented as RGB image. And we have information about also what we do. We sample normals from these surfaces. And basically we can calculate depth just by subtracting position of the camera and these point positions, so we get depth, and that is all you need in order to calculate shading on these objects. So this is VFX code so far. So what we are doing, we have 2 for loops, one for X dimension, one for Y dimension, and you see that resolution is 160 times 120. Resembling something from 90s, and we have input for the camera, and we have what would be the furthest point that ray would try to hit. So what we did, basically the core of this is like we calculate what is the origin point and what is the normal, and we shoot a ray on each of these points into space. So this is that intersect command. And then we sample normals and calculate depth, and that's it. I can send this scene to you if you want to play with it. So, yeah. And next thing was to create some simple shading. Artem was convincing me to do reflections, but no time to do that. Basically, do you know what is dot product? If you don't know what is cross product, okay, you should. Okay, so if we take normals of these points on this sphere, and we take direction of the light, if direction of the light and the normal of the surface, if they are opposite, you get maximum illumination. If they are perpendicular, you get 0 illumination, and all of these parts are negative. You can use them also as well for some effects. Okay, so basically if you do dot product between normal and direction of the light, you get really simple illumination, and this was really high tech in the 70s. Okay, and this is the VFX code that is basically looping through all the lights. I'm giving like points in the space which would represent lights. So I'm looping through all the lights and basically calculating, I don't know where it is, calculating, yeah, so here is calculating dot product, and I'm doing some decay. Decay is inverse square, and that's it. Like, this is really simple thing. Next week in studio, all of our employees will have to write this on their own. Yeah, even shaders. So what this practice teaches you? It teaches you several VFX commands that are really useful. And you're asking yourself, why should there are so many render engines like Arnold, Redshift, Karma, Octane, Unreal. Why should you write render engine? You should do it in order to learn this kind of stuff and this kind of concepts. And if you do shaders in Unreal, if you do shaders in Maya, if you do shaders in Houdini or some VFX in Houdini, all of these principles are something that you will meet along. And I left you links of two really useful tutorials. And now, what are the use cases apart from rendering? So one use case that is really simple is to create snow on objects. So like you can treat snow as like illumination, and in order to get shadowing inside of his mouth, you will need to do this intersect thing. Okay, so this is snow on object. Second thing, this is actual example that we are working on now. We are working on the show in which we have a bunch of these sailboats, and we have a cache for whitewater particles that has 105 million points. We have render farm of 64 gigabyte machines, couple, I will not say how many. Okay, so what is the problem? When we load both, when we load all like cloth simulations, shaders and everything, water surface, we consume around 50 gigabytes of RAM. And then we should load this 105 million points, and consumption of RAM is around 80 gigabytes. So we cannot render it on our farm. So what we need to do, we need to figure out the way to kill all the particles that are obscured by the ship. So what you will do, you will basically cast a ray that's coming from each point toward the camera. If that ray hits something, then delete that particle, because it's behind the boat. Its boat is between that particle and the camera. So we reduced number of points from this to this. So that meant with some other optimizations that we could render it on our farm. Okay. Another thing is, this is also one thing that we are currently doing, is doing these water droplets on the character. So we are using this XYZ dist and prim UV functions that I used for this renderer. Okay. If you saw Avatar, Veta did on the characters something slightly more complicated. Yeah. Yeah. And also, for example, for these ships, what we do, we cannot simulate all of them in the same process, because it's too costly. So what we do, we take 10 of our strongest machines and simulate 10 ships in a row. So we get separate simulations for each one of these ships. And then the question is, how will you blend these different meshes? So we do mesh blending. Actually, we are shooting rays from one mesh to another and trying to find like what would be best middle points in between these meshes. Okay. And the last thing is about matrices. Like today we are going to learn about matrix, and this is what I assumed in high school that I'm going to learn. They gave us a lot of some examples from economics, from trade, and I was totally not interested. And I didn't learn matrices back then, so I had to learn them like 10 years later, unfortunately. Okay, so Miloš already touched on one important principle. That is the principle how Houdini does instancing. So this is image from help. So you see, for example, if you copy these three 3 times, your memory becomes that many times, consumption of memory becomes 3 times larger. But if you instance these trees, you can have millions of these trees, and your memory consumption will not go up dramatically. That's why we can do scenes with thousands of trees, with thousands of characters, with, I don't know, thousands of everything. So instancing is really important principle, and in order to handle instancing better, to control your stuff better, you need to learn how Houdini and basically every other 3D application handles stuff in that way. So on the regular object level, when you manipulate objects, what you are given is these translate, rotate, scale options. And I don't know how many of you animated something. Do you know what gimbal lock is? Yeah, so that is, if you represent transformation in that way, there is possibility that you will get into problem of gimbal lock. So that's one downside of this, but it's really easily understandable. Every artist understands what is translation, what is rotation, and scale. Okay. So, like, if we do some like typical Houdini type of thing, like fracturing this object, and I'm representing these pieces as spec primitives, so each piece is 1 point. So I can move them, and as Miloš showed you, just a moment, yeah, I like opening spreadsheet in this way. So. So as you can see, as I move these points, P attribute gets updated. But when I rotate these points, I don't get any reflectance on attributes in geometry spreadsheet. And that is something that in Houdini, there is no way that you do something on geometry and it is not reflected back on the attributes. So it's somewhere, but it's hidden. And okay. So if you look at the primitives on this geometry, there is one, where is primitive rotation and scale data? So it's hidden inside intrinsic attribute. Intrinsic means hidden, let's say. So we have attribute transform that has 9 numbers. And when I was junior, I was scared of that. What is this transform thing? And so it's actually 3 by 3 matrix. So if I now rotate these pieces, I see that this thing is reflected on that 3 by 3 matrix. And there is also packed full transform, which is 4 by 4 matrix, which contains translation, rotations, and scale, while this previous one contained only rotation and scale and shear. Okay? So I see that my changes are reflected inside of these matrix attributes. So this is like small X code just to visualize what these matrix attributes actually represent. So they represent transformations in a way like X transformation, Y, and Z. And if you know anything about linear algebra, this should be like really easy to you. Okay, and also, like our juniors stumble upon this at some points in production. Like we have animated objects that's coming from Maya, and let's say we want to create bullet holes on these wings, and we need to set these wings into 0 position and then do our effects and then put it back. So you can put it back just by multiplying these point positions by inverse transformation matrix. So, like, that is one thing that every junior in our studio, it comes up to that point, and we are like, aha, now is the time to unlock it. Okay? So, when we put it back together, it stays, it's put back in the place. So, this concept of doing stuff in zero position is really important thing. And if you deal with the characters, there is a lot of effects that, like, you have animated character, but you will do a lot of stuff in the character when the character is in initial position, and then transfer back all of your effects back to the animated version of the character. Okay. Okay, this is the